and how we represent. Okay. So, vector fields, what are they? So, what are we going to do? So, we are going to understand what a vector field is. Look at gradient fields, which is one of the vector fields you already know, but I never, well, actually, I think I mentioned back when we covered the gradient. That's actually what's it called? A vector field, and it's also a conservative vector field. We'll talk about those conservative vector fields, but well, how are these vector fields different from from the vector valued functions that we discussed earlier? Well, so back at the beginning of the course, we look at vector valued functions for which the variable is only one variable, t. That means, well, for simplicity, we describe those functions as the position of an object traveling along that curve in space or in the plane. It doesn't matter. It could be either. It could be either one at different times, right? So that's position at different times. Now, these vector fields, those are going to be functions of 2 or 3 variables, but what are they? In this case, they're going to be x and y. The components of these vector fields are no longer going to be an x of t, y of t, and z of t. No, in this case, these components are going to be functions of x and y and functions of x and y. But what are they anyway? I mean, these vector fields, for instance, if you focus on a point, you will have a vector pointing or having components containing those coordinates. But well, how do we describe them? These are no longer the position at different times. For instance, we can think of streamlines, for instance. You know, when you're traveling, say by boat, for instance, you're in a boat. You're going with the current or against the current, right? So if you're going with the current, you have a bunch of vectors, of some velocity vectors by the river, you know, helping the boat go faster, or vice versa. If you're going against, you're going to struggle to move on because you're against the current. Or when you're traveling by plane, or you're flying from west to east, typically the flights are faster than coming back because of the direction of the air. So in the direction towards the east, you're going with the wind, while coming back you're going against the wind. So have you noticed that? Sometimes a flight, say to New York, is like 5 hours, but when you're coming back, it's almost 6 hours. That's because you're coming back against the wind. So, so we're going to describe those vectors as a vector field, multiple vectors acting on an object. For instance, we're having an object traveling along a curve, for instance, but then we have this driving force described by these vector fields, and that driving force may help the object move faster, like the case of the airplane or the boat, or keep it from moving, and that's like the against the wind or against the current. Let's talk about these vector fields and see how can we represent them. All right, so sketch some vectors in the vector field given by f of x, y equals x in the direction of I. All right, let me write this vector field first of all in component form. Well, number one, this is the same as saying, what's that? Xi plus 0j, which is the same as saying x0, right? So that means this vector field, it's describing vectors that are going to go in the direction of the x coordinate only, and 0 for the y component. Well, I'm going to sketch some vectors in this grid right here. So I'm just going to get some random points here. Say the point 1, 0, 1, 1, negative 1, 1, negative 1, negative 2, 3, 0, 3, 1, okay? We don't have to plot infinitely many vectors. Just a few are more than enough. Okay, so how are we going to go from order pair to vector? Well, the vector field, these vectors are the result of having the x component of the vector to be the x coordinate in this case. And in this case, the y component of the vector, they're all going to be 0. So we can fill in the zeros here. and simply copy the x component, the x coordinates to be the x component. 1, 1, negative 1, negative 1, 3, 3. All right? How about we plot these vectors and see if we can see a pattern? All right? So the vector 1, 0 at top, number 1, I'm going to go to the point 1, 0, okay, and from there I'll start. That's going to be my initial point, and then from there I'm going to start and plot the vector 1, 0. That's the vector at that point. Let's go to the point 1, 1. What vector do we have at the point 1, 1? The same, 1, 0, right? Let's go to the point negative 1, 1. That is that point. But what vector do we have? Don't we have the vector negative 1, 0? So go negative 1 in the x direction, 0 in the y direction. Let's go to the point negative 1, negative 2. Okay? That's the vector. That's the same vector, negative 1, 0. What else? Let's go to farther points. 3, 0. Okay? To the point 3, 0, which is this point right there. And I'm going to plot the vector rather, 3, 0. 3 units in the x direction, 3 units in length, but 0 units in a vertical length. Lastly, at the point 3, 1, I'm going to plot the same vector. Alright? I'm going to plot the same vector. Okay, so how about we see this in GeoGebra, because it's gonna give us a better visual, because plotting a bunch of vectors is simply not that practical here. Okay, so vector field 2D. Oh no, I need to drag it. Okay, so I would need to let me change this component. So the P component, that's just x, and 0 for the y component. What do you see? So we have all vectors pointing in the horizontal direction, in the positive direction for all those points in the to the right of the y-axis, and the opposite for all the points on the left-hand side of the y-axis. Well, let's see how can we modify this. Okay, the extent maybe. Okay, that's how many vectors. The scale, we can scale these vectors. How about the spacing? No spacing, more spacing. But this is what we see. We see a lot of these vectors going in the opposite direction. Maybe this y-axis, it's a magnet, right? Maybe it's a magnet, and these arrows right here represent the opposite pole of the magnet, right? So again, also those magnetic fields, electrical fields are also can be represented by this vector field. So not just the winds, the streamlines like that. So let's have a look at another example. This one, don't save. Okay. On the next page, we have another vector field, negative y, I, x, j. That means, in component form, negative y, comma, x. What does that mean? That for every order pair, for every point on the grid, the vector will be obtained by having the x component, that is the negatives, the opposite in sign of the y coordinate, and the y component is just the x coordinate. I'm gonna write a bunch of other points here. That is 1, 0, 0, 1, 2, 0, 0, 2, 0, negative 2. Okay, that's enough. That's enough. Oh wait, negative 2, 0. I was supposed to do negative 2, 0, and 0, negative 2. Okay, be careful when writing down the vectors. Okay, so the x coordinates are going to go to the y component. So let's do that. 1, 0, 2, 0, negative 2, and 0. While the x components of the vectors are going to be the opposite in sign of the y coordinates of the points. Okay, that is, okay, the opposite of 0 is 0, of course. Then that's negative 1, that's another 0, negative 2, and that's a 0, and that's negative, negative 2, that's positive 2. All right? Let's plot these vectors by hand at those given points. Well, let's see. Let's go to the point 1, comma 0. And from there, I'm going to plot the vector 0, 1. Isn't that this vector pointing up? What about at the point 0, comma 1? Okay, I'm going to go to the point 0, 1. And what's the related vector? Isn't that the vector negative 1, 0, which is this vector here? Right? What about at the point 2, comma 0? Okay, let me go to the point 2, comma 0, which is this point. What is the related vector? Isn't that 0, 2? That is a vector with magnitude of 2 pointing up. All right? And what about at the point 0, comma 2? What about the point 0, comma 2? 0, comma 2. That is the vector negative 2, 0. One more, or a couple more. At the point negative 2, 0, I'm going to have the vector 0, negative 2. At the point 0, negative 2, which is, at the point 0, negative 2, which is this one, I'm going to have the vector 2, 0. Let me do another point. Let me do 3, 4. No zeros like the other points. And see what we get. Okay. So the related vector will be the opposite in sign of the y coordinate and the x coordinate. Okay. So let's go to the point 3, comma 4. And from there, I'm going to plot the vector negative 4, positive 3. That is this vector right here. All right. Okay, look at these vectors. What did you notice about this vector? What does that represent? If this were, I don't know, maybe a magnetic field or a streamline or something, what does that look like?
Looks like something spinning.
Something spinning, right? Yeah, well, yeah, it looks like spinning. Okay, let's go GeoGebra. Let's go to GeoGebra and see what it is about. Okay, so that is negative y and x. Yep, it's spinning, right? Of course, we don't have to plot all these infinitely many vectors, right? So yes, there's a special name for this kind of vector field, by the way. This is called the rotational vector field. Or also it's called radial vector field. There's a special name. All right. Let's see. No, I don't want to rush through the next examples. 4 minutes before we finish.